Section 6.4, exponential growth and decay. We're going to start with two vocabulary terms here, exponential growth and exponential decay. Basically the same type of definition. Growth meaning you're getting bigger, so it's an exponential function. Remember, we're multiplying our y's each time, where y increases as x increases. So as we go farther down the line, if we think about the number line, as we go to the right on the number line where x is getting bigger, then our y values are going to get bigger. Okay, if it's exponential decay, as x gets bigger, y is actually going to get smaller. So that would be one of those functions like where we are, dividing by 2 or multiplying by 1/2. It's the same thing. That would be an example of exponential decay. Okay, exponential growth and decay really has a lot more real life application than some of the previous sections. So we start with this exponential growth and decay model. Okay, so here's our formula: y equals a times 1 plus or minus r to the t power. Now your y value represents your final amount. Okay, so we'll write that in: final amount. That is this letter right here. Now your a value, this one right here, is what you're starting with. It's your initial amount, or you can put starting amount. Now, either one is fine. Initial amount. Okay, the r value, this number right here, r represents your growth or decay rate, depending on the type of problem. Growth / decay rate. And this needs to be written as a decimal. Okay, we'll talk about that here in just 1 second. And then the final variable here is t. T represents, just like it usually does, represents time. Now it could be in years, could be in weeks, could be in hours. It's really going to depend. Usually t is represented in years, but that's not always the case. In the type of problem that you're going to be working with, it will tell you what your time is measured in, whether it's years or days or weeks or hours. Usually it's years, but it's not always years. Now I said, going back to this growth or decay rate as a decimal. So let's just say, if it was growing by 3%. 3%, to turn a percent into a decimal, we're going to take the decimal point, which is right there, right after the 3, and we're going to go 2 places to the left. Okay, so our decimal point now becomes there. Since we have a space right here, what we're going to do is we're going to fill in a 0. So 3% becomes 0.03. So I'm going to get rid of all of that business. We're going to say 3% as a decimal is 0.03. And you don't necessarily need this 0 because that really doesn't matter. It's just a placeholder, but you definitely need 0.03. If we wanted, 10%, if we move the decimal place two places to the left, we start here, 1, 2. 10% can be written as 0.10 or just 0.1. Okay, so just keep that in the back of your mind. If we want to go from percent to decimal, which we need to do to put it in here, then we have to move the decimal place 2 units to the left. Okay, so let's do a couple of examples here, a couple of story problems. Oh, before we do that, I missed one thing. The sign right here, the plus or minus. If this scenario is growth, okay, I'm just going to write this off to the side. If it's a growth problem, we're going to use plus, and if it's a decay problem, then the symbol we'll use is minus. We're never going to use both, but the formulas for growth and decay are just exactly the same with the exception of this sign. So rather than write it out twice, we usually just write it once, and then since this is the only difference, we just need to know which one to use. So if it's a growth problem, if we're getting bigger, we're going to use plus. If it's a decay problem where we're getting smaller or we're losing value or losing people, then it's going to be a minus. All right, so let's do a couple of examples here. The inaugural attendance at a music festival is 80,000. The attendance Y increases by 6% each year. So task number 1, write an exponential growth function that represents the attendance after T years. So we're not going to get an actual number here. We need to write a formula. We'll do that in red. Well, what do we need to know? Well, we know 80,000 is the inaugural, means the same thing. So this is going to be our A value. We've got another one here, 6%. That is going to be our R value, our growth rate. And remember, we need to turn that to a decimal. So 6% as a decimal is going to be 0.06. We're going to move that to the decimal place 2 units to the left. Okay, we don't have a T and we don't have a Y. We don't have a time yet. It just says after T years. Okay, and the final amount, usually we don't know that until we are given a length of time. So let's go ahead and put everything together. So remember the original function, y equals a times 1 r to the t power. What symbol goes here? What goes in between 1 and r? Since we're growing, we're increasing, then we're going to have a plus. It's going to be 1 plus, let me try that again, plus, a little better, y equals a times 1 plus r to the t power. Let's plug in everything that we know. We'll do this in green here. So we don't know y, we do know a, that's 80,000. 80,000 times 1 plus, we do know r, that's 0.06, but we don't know t, so we're just going to put the t power. Now, if you want to simplify this, do 1 plus 0.06, which I believe the any big ideas assignment would want you to do that. We certainly can. So that'd be 80,000 times 1 plus 0.06 is 1.06 to the t power. Now, on a quiz or a test, I am perfectly fine with this line, but like I said, for big ideas, it's going to want you to simplify it down into 1.06. Question number 2, about how many people will attend in the 5th year. So now we're given a time, 5. We're going to plug everything in, so we're going to have y equals 80,000 times 1.06 to the 5th power. And you can type this in exactly like this on your calculator. You don't even need to worry about the order of operations because your computer or your calculator will do it for you. Okay, so when we're going to type this in our calculator, we're going to go 80,000 parenthesis 1.06, or if you want to do 1 plus 0.06, it doesn't really matter. And then we're going to hit the exponent button and then 5. And that's going to give us our answer. And we want to round to the nearest whole number because we can't have half a person. Okay, that just doesn't make sense. So our answer here is going to be approximately, and there was a decimal here, I'm rounding to the nearest whole number. This is going to be 107,058 people. Okay, that is how many should be attending roughly in the 5th year of this festival. Let's try another one here. Our website has 150,000 members in 2010. The number of members increases by 15% each year. All right, so question number 1, write an exponential growth model to represent the membership T years after 2010. So this one's a little bit different. We still have our initial amount, 150,000. Okay, so we'll just kind of lay this out. A is equal to 150,000. Our growth rate is right here. So 15% as a decimal is going to be 0.15. Now this is where people get confused. It says in 2010. This really isn't a year or a time. This is just giving context to this situation. Okay, so really we don't have a time yet. It doesn't give us one. That's what we'll get here in question number 2. So let's fill in what we know. Again, growth model, y equals a times 1 plus r to the t power. Plug in what we know. We know a and we know r. And those are the only two things we're going to be able to plug in. So we're going to have y equals our growth rate, or sorry, our initial amount, 150,000. That's 15,000. There's 150,000. Whoa, sorry about that. Flip the page. 150,000 times 1 plus our growth rate, 0.15. And we don't have a time yet, so that is going to be t years. And that's going to be your answer there for question number 1. Again, if you want to simplify that, 1.15, feel free. It's not necessarily required. Question number 2, how many members will there be in 2016? Round your answer to the nearest 1,000. Okay, so our rounding is going to be a little bit different, but we can certainly do this. All right, so 2016, so that's going to give us our time. Okay, in 2016, it says T is the number of years after 2010. Well, how many years have passed between 2010 and 2016? That would be 6. Okay, so T is going to be equal to 6, and we're going to take that and put it right there in our original equation. Okay, so let's write this out. Y equals 150,000 times 1.15 to the 6th power. Again, this is something you can type in your calculator. When you get this, you're going to get roughly 346,959.11. But again, you can't have half or a decimal worth of a person, so we're not really going to worry about that. But the directions do say round to the nearest 1,000. So the 1,000 place is this one right here. So we're not actually rounding near the decimal. We're actually rounding kind of far away from the decimal. So when we round this, we look at the 6, we look at the number after it, and the 9 definitely is going to make it round up. So we're going to say roughly 347,000 members in 2016. That's going to be our answer there for question number 2. Let's try one more here, one more story problem. The value of a car is $21,500. It loses 12% of its value every year. All right, well, $21,500, that's going to be our A value. 12%, this is going to be our R value. We can say R is equal to, we need to turn that to a decimal, so that's going to be 0.12. And again, we don't have any other time, so write an exponential model. So we're going to say y is equal to our initial amount, 21,500, 1, and our R value is 0.12 to the t power. Now this one's a little bit different because we are losing value every year, and cars definitely lose value every year. 12% is probably pretty accurate, actually. So if we're decreasing in value, we're going to use minus this time instead of plus. The first two examples we used plus because we were growing. In this example, we're using minus because we're losing value. We're decreasing the value of the car as time goes on. So now question number 2, estimate the value of the car after 6 years. We can plug in 6 for our time right in there, and we'll get our answer. So we'll say y is equal to 21,500 times, if you want to do 1 minus 0.12, feel free. If you don't know what that is, you can use your calculator. It is 0.88, and we're going to raise that to the 6th power because it's 6 years. Okay, again, this is something, just type it right into your calculator. When you do this, make sure you round your answer to 2 decimal places, because money is always rounded to 2 decimal places. So maybe jot that down off to the side. Money rounds to 2 decimal places. Okay, always. Money always rounds to 2 decimal places. So when we do this, type 21,500 times 0.88 to the 6th power, or you could do 1 minus 0.12. Either one's going to be fine. Make sure it's in parentheses. What you're going to get is the car is worth $9,984. That's a really bad 84. Let's try that again. $84.69. Okay, make sure you always round to 2 decimal places when we're talking about money. We should probably put a dollar sign here. Ooh, let's try that one more time. Dollar sign, because we are referencing money. So how do you tell the difference between growth and decay if you just were given an equation? Well, if we think about the exponential function from section 6.3, so that's y equals a times b to the x power. How do you know whether it's growth or whether it's decay? Well, that's where we need to look at our b value. So this one right here. So I'm going to underline this here in blue. So if the b value is bigger than 1, then we can say this function is exponential growth. Okay, if your b value is bigger than 1, then it's exponential growth. Now, if your b value is between 0 and 1, then it's going to be exponential decay. Okay, exponential decay. That's a really bad A over there, but we'll make it work. Exponential decay. Okay, so that's what we need to look at when we're determining whether something is growth or decay. Now, if we go back to the beginning, go back to this definition here, as y increases, that's growth. As y decreases, that's decay. So in these first 4 examples here, okay, maybe the last 4 examples, my bad, we need to look at the y values. But we'll start here with these equations. So determine whether each table or equation represents exponential growth or decay. Okay, what we need to look at here is the value of the base with our exponents. So whether it's 1.07, 1.01, 0.81, or 0.99, that's what we need to. That's what's going to be used to determine whether it's growth or decay. Now the numbers out front, 5.2, 4, -3, none of those matter. Those don't determine whether something is growth or decay. Okay, it's always the number with the exponent. Okay, since 1.07, I'm pretty sure is bigger than 1, so we can say that this one is exponential growth. Okay, 1.01, also bigger than 1, barely bigger than 1, but it is bigger than 1. This one is also exponential growth. Okay, again, with number 3, we're looking at the number with the variable. 0.81 is between 0 and 1, so this is an example of exponential decay. We're going to get it smaller and smaller as time goes on. And 0.99, while it's very close to 1, it is less than 1. Okay, this one is also exponential decay. Okay, so if your base, the number with the variable, whether it's x or t, doesn't really matter. If it's bigger than 1, like these two, it's going to be growth. If it's between 0 and 1, it's going to be decay. All right, let's look at the tables. These are going to be a little bit different. We can see, like in this one, we're definitely getting smaller, but in order for it to be exponential, we need to be getting smaller by the same rate. Okay, we need to be like dividing by 3, or dividing by 5, or dividing by 2, or dividing by 10, something like that every time. Okay, so if we go from 270 to 90, if we just drop the zeros, that would be 27 to 9. We can do that by dividing by 3. And 90 divided by 3 is also 30, or 90 divided by 30 is also 3. 30 divided by 10, again, we can get there by dividing by 3. So this one is an example, since we're getting smaller by the same rate every time, this is an example of exponential decay. We're getting smaller as time goes on. With number 6 here, we need to go from 5 to 10. 5 times 2 would be 10. 10 times 2 would be 20, so times 2. 20 times 2, that would be 40. Yeah, 40, not 4. Whoops, my bad, I was thinking about 40 times 2. So we're getting bigger as time goes on. We're getting bigger by the same rate as time goes on. This is an example of exponential growth. Okay, let's look at the next one, 64 to 16. Oh boy, if we take 64 divided by 16, that's going to give us 4. So we can go from 64 to 16 by dividing by 4. 16 divided by 4, that would give us 4. And 4 divided by 4, any number divided by itself, is going to give you 1 every time. So we're getting smaller as time goes on. We're getting smaller by the same rate as time goes on. So this is an example of exponential decay. Now with this last one, our y's aren't, or our x's aren't going up by 1s, but they are going up consistently, so that is okay. To go from 4 to 11, 4 times, I have no idea what 4 times something is to get 11, but I do know that we could add 7 to get to 11. And if we look at the next pair, 11 to 18, that's also going up by 7, and 18 to 25, that's also 7. But remember, for it to be exponential, we have to be multiplying or dividing by the same amount, not adding. This would be an example of a linear function. So it's neither exponential growth nor decay. So we can write neither for this one, because we're adding 7 every time. We're not multiplying by 7 or dividing by 7. We need to multiply or divide each time to have an exponential function. It doesn't matter if it's growth or decay. Since we're adding, this is a linear function. That's not even close to what the question was asking. The other big real life example, or real life use of exponential growth and decay, is the idea of compound interest. If you have a bank account, you have been involved with compound interest, whether it's a savings account or a credit card or a loan. Some of you probably haven't taken out loans yet, but you might have a bank account that your parents started for you. That is an example of where compound interest is used. The formula for compound interest, A is equal to P times 1 plus, it's always plus, R over N to the NT power. Okay, it's kind of a complicated formula, but if you can kind of get used to it, it does kind of roll right off the tongue. We have lots of variables here, A, P, R, N, and T, and here's what they all mean. Okay, so A is your account balance. It's what your, like if you were to look up your account online, that's the number you would see when you look up your balance. P is your initial deposit, or it's called the principal. That's why it's labeled P, principal. It's the initial deposit. It's what you initially put in the bank. Okay, your R is your interest rate, and again, your rate needs to be as a decimal, so if you get 6%, that needs to be 0.06. The one people struggle with initially is your N value, the number of times interest is compounded in 1 year, okay? So if we said like quarterly, that would be an N value of 4. Or if we said weekly, that's a really bad weekly. Let's try that one more time. Weekly, that would be 52, because there's 52 weeks in a year. If we said monthly, that would be 12, because there are 12 months in a year. And we could also use, you might see daily, that would be 365, because there's 365 days in a year. So those are going to be your most common N values, 4, 52, 12, and 365. Those are going to replace your N there and there. And we can use your calculator here to make this go a heck of a lot faster, and instead of trying to figure out what this is, and then simplify it, we can use our calculators to do this a whole lot faster. So, got one example here. You deposit $100 in a savings account that earns 6% annual interest, compounded monthly. That's going to be a key piece of information. So if it says it's compounded monthly, that tells us right away that our N value is going to be 12. Okay, what else do we have? We know $100, that would be our initial amount, or our deposit, so that's going to be P, that's our principal. And we also are given 6% interest. Now, it does say annual interest, but it's not going to be compounded annually. It says compounded monthly. The 6% is the amount of interest you get over the course of the year. And how they do interest, if you get 6% annual interest, they're going to take 6% divided by how much, or how many times they pay you interest. So you're going to get 1/12 of 6% every month. You're not going to get 6% every month. You get 1/12 because they divide it by 12 of 6%. Okay, we aren't given t yet, so we're going to need to write an equation first. So let's do that here in purple. So I'm going to kind of scroll back and forth. So our A comes first. So our account balance is equal to our principal. So that's $100. I was about to write P. 100 times 1 plus. Now we have our R value, and that's 6%. So that needs to be a decimal. So 0.06 divided by N, which is going to be 12. Close the parenthesis, and then we got NT power. So our N value again is 12. These two numbers right here are always going to match because they are the same variable up there. Okay, so we have 0.06 over 12 to the 12 times T power. And I'm perfectly fine with you leaving your answer just like this. If I say write an equation and write a function that represents the balance, I am perfectly fine with this because this shows me you know exactly where everything goes and what everything represents. Last question here, find the balance after 4 years. So we can type this line right into our calculator. The only change is we're going to make T4. So I'm going to write that out here in blue. So we're going to say A is equal to 100 times 1 plus 0.06 over 12 to the 12 times 4 power. And now, if you want to clean this up, you certainly can, but you don't have to. We can just go ahead and type this in our calculator straight away. How this works, we're going to do 100 parenthesis 1 plus 0.06. I'm going to do this all in one line. So 0.06, and make sure you use divide. Don't use the fraction button on your calculator. Over 12 parenthesis, raise this to the power, and in another set of parentheses, we want to do 12 times 4. Now, if you know 12 times 4 to be 48, you don't necessarily need parentheses. We can just raise it to the 48th power, but we do need to multiply these two numbers first. And if you're just going to leave it with the multiplication, you do need parentheses because you need to tell the calculator do this before this becomes an exponent. Because if you don't put parentheses, it's going to do this, raise it to the 12th power, and then multiply it by 4. You're going to get a much, much, much bigger number than what you should have. Okay, this is the way you're going to type it in the calculator. Do not use the fraction button or on your calculator there. You have to use the divide button, and then make sure you're using a couple of sets of parentheses. When you do this, since this is money here, okay, so we do need to round to two decimal places, so your account balance is going to be $127.05, okay? That's going to be your final answer. That's what you would see, if you plugged in $100 into a savings account getting 6% interest compounded monthly. If you waited 4 years and then looked up your balance, this is what you would find.